We're going to demonstrate using velocities from a triangle of GPS sites to investigate crustal strain. We start with three imaginary points. For each point we have the east-west coordinate, or the longitude, the north-south coordinate, the latitude, the east-west velocity, usually measured in millimeters per year, and the north-south velocity, also measured in millimeters per year. Here are our three sites. They form a triangular area. For each of these sites we have the north-south velocity and the east-west velocity represented by these blue arrows. All three of these sites are moving towards the north. Two of them are moving towards the west, and one is moving towards the east. When we add those blue vectors together for each site, the result is the black vector, which is the total site velocity vector for each site. Now, just looking at these, we can tell that these three sites are going to change their relationship to one another, their spatial relationship to one another over time. That is to say, the triangle that we see at the beginning of our experiment that connects those three sites as the apices of the triangle is going to have to change its shape in order to follow those velocity vectors over time. In order to do this analysis, we find the center of the triangle as it exists at the beginning of our experiment. We reestablish a coordinate system that is based on the center of that triangle at the beginning of the experiment. And we imagine that inside of the triangle is a circle that is a rigid part of the triangle. That is to say that as the triangle distorts, the circle distorts. We find the translation vector first. The way we do that is we add the three site vectors together and find the average of those three. So we add the vectors together and divide the result by 3. That gives us the vector that you see extending from the origin of our coordinate system in the center of the circle. So the idea is that over time that triangle would translate, and as it's translating, it's distorting and perhaps rotating in a way that looks like this, more or less. What we can then do is take that translation vector and subtract it, and so move our distorted triangle back to the middle so that the middle of the ellipse is in the center of the circle. The ellipse that you see superimposed on the original circle is the horizontal strain ellipse for this experiment. It has a red line indicating the maximum strain axis and the blue line indicating the minimum axis of the strain ellipse. If we were to back this experiment up and paint those lines into the ground surface at the time that that triangle was distorted, and then stick the crust in our Wayback Machine and go back to the beginning of the experiment, those painted lines would look like this. And as you can see, those lines have rotated, and that rotation is an important component of the strains. So this is our original state, and this is the distorted state.